Hello and good afternoon, everyone. Welcome to the day 3 of Epsilon 2021. I am Aditi Rao, PR mentor at IEEE SIESGST, and I welcome to the third panel discussion for the day, which is being conducted under the MTTS track of our event. This is our third session for today, where our invited guests will be navigating around the theme of MTTS Track, which is the exciting and emerging domain of quantum computing and its multiple aspects. Let me now introduce you all to our moderator for this panel. We are pleased to have here with us Mr. Syed Farhan Ahmad, who is a quantum research intern at UCLA. He is also the founder of Q Power Community and also a Microsoft Gold student ambassador.
Hi Aditi, thanks for having me here.
Hi, hello, sir. Welcome to the session. Now, let us now move further and introduce you all to the invited panelists for the discussion. First up, we have Ms. Shalaka Verma, who is a director at Partner Technology at Microsoft. She is also an ex-IBM Q ambassador and also a director at IBM Sales Technology. Welcome, ma'am. We are extremely honored to have you with us. Next up, we have Ms. Kavitha Yogaraj, who is an quantum computational scientist at IBM. She is also an IBM quantum ambassador and Qiskit advocate. Next up, we have Mr. Shesha Raghunathan, who is also an IBM ambassador, quantum distinguished ambassador, as well as advisory R&D engineer at IBM. As the fourth panelist of today, we have here with us Mr. Arun Pati, who is a professor at Harishchandra Research Institute, as well as a member of Quantum Information and Quantum Computational Group under the same institute. Last but not least, we have here with us Mr. Eraraya Ricardo, all the way from Indonesia. He is a Qiskit advocate as well as a final year student at Quantum Technology Lab at the Bandung Institute of Technology. I'm sure by now the audience can't wait for the exciting discussion to begin. And because I surely can. So without any further ado, I would like our moderator, Mr. Syed Farhan Ahmad, to take over for the further proceedings and initiate the much awaited quantum discussion.
Thank you for the wonderful introduction, Aditi. Okay, before we get started, let me just tell you what are the different topics that we're going to cover in this session. So we'll be touching upon quantum computing with microwaves, specifically with superconducting qubits. Then we'll be talking about different innovations and applications of quantum computing in today's era. Of course, we'll also be discussing about the future scope of quantum computing. So before we actually begin, I would request all the panelists to introduce themselves in a way, so that they can talk about their journey in quantum till now, their area of research, or the domain of work in quantum, or the motivations that have kept them going every day. Shesha, sir, would you like to go ahead?
Hi all, my name is Shesha Raghunathan. I'm part of IBM's hardware labs. My PhD was in quantum computing, and then when I moved back to India, I joined the hardware labs. I'm part of the team that develops tools and methodologies to design microprocessors. I'm also, given my background, I'm also ambassador. What that is evangelist for the technology. I'm a distinguished ambassador, and I'm also working with India Research Labs to form a research team on quantum computing.
Thank you, Shesha, sir. That was a wonderful introduction. Shalaka, ma'am, would you like to go next?
Sure. Thank you, Syed. And good afternoon, everyone. All the listeners who are joining in on a Sunday afternoon. First of all, thank you so much for taking time out. Thank you, co-panelists. Myself is Shalaka. I lead the Partner Technology Cloud Solution Architect team from Microsoft. I come here from IBM and I picked up quantum computing in IBM as one of the passion area. It's more like a self-starter journey that I had. Here at Microsoft, I actually am responsible for landing Azure Quantum on top 16 partners that are based out in India and serve the customers globally. And more or less, I think my journey into quantum is really about seeing the technology coming alive with the customer use cases, and I'm a lot connected into the technical sales side of the profession in the journey, folks. Thanks.
Thank you, ma'am. That's indeed a wonderful profile. Arun sir, would you like to talk about your journey and your areas of research?
Yeah, so myself, Arun Pati, from Harishchandra Research Institute at Allahabad, and here we have one of the largest group in India in quantum computing. So my journey has been almost more than 30 years in this field. So I started working quantum information in 1990s, and then quantum computing. So when I started my journey, there was absolutely no one in this field working. So my so-called supervisor, he was telling, "Why do you want to work in this topic? There is no future in this topic." So with that kind of remark, I started my journey, and I pursued my interest and my explorations, and so we do a lot of things. I mean, mostly we do theoretical work, but once in a while we do collaborate with people with doing experiment also. So I collaborate with like in Eraraya or also in China. So I do have many collaborations. Yes.
Thank you, sir. You must have had a lot of motivation if you started in the
Yeah.
1990s,
Self
especially
motivation.
with
Yeah.
quantum.
Self motivation only.
That's really awesome, sir. That's really awesome. Okay, Kavitha ma'am, would you like to go next?
Hi, everyone. Thanks for joining on Sunday afternoon. It's a long weekend, most likely here in India, and a lot of you have joined here. Thank you for that very much. I am a quantum computational scientist working in IBM. I'm also a QSKIT advocate, a quantum ambassador. So I work in GBS. I also work with Shesha Raghunathan in one of his research labs group, IRL group. So here in GBS, what I am trying to do is implement quantum, the QSKIT into applications, trying to solve clients' problem. So that is my area of work. And before coming into quantum, I was working as a solution architect in cloud computing, Kafka, and big data applications and data science. So my merger was big data and data science, and then putting that in Docker containers and in cloud. So that was a cutting edge technology what I was working on. And then 2 years ago, I got introduced to QSKIT. That's when I actually was very much interested in QSKIT. Started exploring QSKIT myself, and have a lot of questions on Stack Overflow, how to do this, and started doing GitHub pull request for QSKIT. That's how I got into quantum, and I'm a full time as a quantum computational scientist in one of the IBM quantum teams. Thank you.
Thank you, ma'am. That's indeed a great industrial experience you have there. Ricardo, would you like to go next? Would you like to talk about your journey in quantum till now and your areas of research?
Sure. Thank you. So it is a big honor for me to sit here with many researchers who already have a lot of more experience than me. So I actually just started my quantum journey about 1 or 2 years ago. So I deep dive into this quantum realm because I feel it is a very exciting field, and I would like to take it for my thesis work. So I just recently finished my thesis in quantum machine learning, where I developed variational quantum circuits to convolve and classify images. And I'm looking forward to learn more from all the panelists here also. Thank you.
Wow, Ricardo, computer vision with quantum computing is something I'd like to try. Let's catch up sometime later on.
Mm-hmm.
Yeah. So talking about myself, I was introduced to the field of quantum computing during the Vijoshi camp as part of the KVPY IAC program. And after that, I also interned at IBM India Research Lab under Shesha sir. And right now, I'm working at UCLA as quantum research intern, mostly working on quantum optical control. Quantum optimal control. All right. So to begin with the questions, the actual discussion, let's start off with what is actually a quantum computer. For those of you who weren't present in yesterday's and day before yesterday's sessions by IBM, well, quantum computing is nothing but a new paradigm of computing, right? I mean, it's better if we can hear this from the experts. Shesha sir, would you like to go ahead and talk a little bit about how this paradigm is different from classical computing?
Right. So classical computing, as you all know, operates on bit strings, which is sequence of zeros and ones. The value of the bit string at any point in the compute is always fixed. It's going to be some sequence of zeros and ones. Quantum, on the other hand, is very different at that basic level in that the basic element of compute is called a quantum bit or a qubit. And that qubit is not necessarily 0, 1, but a combination of 0 and 1 in a probabilistic sense. So what that has done is a computation which the way it is fundamentally deterministic. In that you get some input, you will get certain input in some fashion. Along the way, you will always have the sequence of values that you can always track. But in quantum, it is at a fundamental level probabilistic. Without going too technical, I think that basic fundamental difference is what is driving a lot of these things. Plus, the reason for the name quantum is naturally because the rules of the game is determined by the postulates of quantum physics. So it sort of is an extension of quantum physics. And therefore, you have a computation that leverages the principles of quantum physics, which in a way fundamentally is probabilistic. And we try to do computation using those principles.
Thank you, sir, for the insights. I mean, what type of problems are quantum computers good at solving? Are they really good at solving any kind of problem, any kind of universal problem better than classical computers? Arun, sir, if you'd like to talk about this.
Yeah, so, when the idea of quantum computing came, it was not very clear in what way they are more efficient, more powerful. So that's how the original discoverer, David Deutsch, and along with Richard Josa, they tried to design the first algorithm, so-called Deutsch-Josa algorithm. And that was the first example where, some suitable function can be tested in a quantum computer exponentially faster than any classical computer. And later on, as you know, so-called the Schwartz algorithm, Grover's algorithm, all these things came. So it is not true that quantum computers can solve all the problems efficiently and in a much faster way compared to classical computers. No, that is not true. That is a misnomer. So you have to figure out. You have to do your, you have to cleverly design your algorithm and find problems which can be solved efficiently in a quantum computer. So that is one of the hard challenge. That is why over the last 30 years, even though the idea came in 1985, still we don't have many quantum algorithms yet. We have only a handful of problems which can be solved. But having said that, whatever things we have discovered, we can try to utilize those and try to see, try to apply in variety of other areas and see what can be done. So the short answer is quantum computers cannot solve everything much faster compared to classical computers. So you have to design, you have to cleverly find out, you have to discover new algorithms which can be done more efficiently, more faster. So that is the hard part of the research. Yeah.
Thank you, sir. Shalaka ma'am, would you like to touch upon a few applications of quantum computers in today's era?
Yeah, so I mean, there is no application in today's era, honestly, but there is scope for a lot of, right? The way I'm looking at it right now is you can broadly classify them into a set of optimization problems and the set of problems which really need circuit-based algorithms at the back, right? Now, the optimization problem in itself really touch bases upon a huge number of use cases across industries where right now there is a lot of optimization in this. So right from looking at supply chain optimization in manufacturing to maybe vehicle route optimization in automotive, to a portfolio optimization in finance, to a power grid optimization in energy. All of this, right? So one common theme, but you have different kinds of use cases across industry with that one common use case coming in picture, common algorithmic breakthrough coming in picture. Quantum chemistry in itself, I think it's a broad topic which has got good potential on quantum computer. And again, the entire healthcare, pharma, even the paints, there are a myriad of these industries like precision medicine, which can benefit from just solving that one core problem. So the potential I see is huge, but we have a lot of time to and the progress to be made for really mainstreaming a lot of these applications.
Thank you for the great insights, ma'am. Okay, talking about quantum communication or quantum cryptography, I mean, it's a direct application of quantum computing, provided that, ISRO has made this recent breakthrough demonstration of free space QKD over 300 meters. It's indeed showing that, where quantum communication is going in the next 5 years or in the near future. Arun sir or Shesha sir, would you like to touch upon this particular topic?
Yeah. So quantum computing is a part of the big picture that is quantum information. So quantum information is the bigger area of research, which is quite vast. So under that we have quantum computing, quantum communication, quantum sensing, quantum metrology, variety of things are happening. And as you rightly said, quantum communication has really progressed a lot, not only in quantum key distribution but also like quantum teleportation and long distance entanglement distribution. So as you might have seen in news for the last 2 years, China has already distributed entanglement over say 2,000 kilometers. So that has a lot of promise, and it has been also commercialized, and many private companies similar to private companies working in area of quantum computing. Quantum communication also has progressed a lot over the last 3-4 years, and I would say that even over the next 5 years, quantum communication will be even it will really touch even common people. That is the big hope. Yeah.
Thank you, sir. Shesha sir, would you also like to touch upon this? It's all right.
Right. So I think pretty much key parts was covered by Professor Pati. I'll just add a few things from an industry standpoint, and particularly from, say, an IBM standpoint. The compute model that we are essentially looking at this time is cloud-based, which means that you're gonna likely to have these hardware residing in a cloud, and then you're gonna have some way of leveraging that to do compute. If you see the natural extension of that in time is working towards a quantum internet type framework where you can transmit quantum bits across the network, but that's a little further out. I think communication technology, what it's currently doing is perhaps in terms of application in direct industry application is probably further along. But I think the technologies and the knowledge that we're going to gain from there is probably going to feed into the broader theme of computing if you want to consider internet as a broader theme in time to come. I think some of those things will feed into those technologies. From IBM standpoint, of course, our attention is on the compute side, which means we are more focused on building the systems and the solutions that can leverage the hardware. But the other technology will intersect with the main hardware or the compute side in time to come when you have quantum internet coming in.
Yes, indeed, sir.
I would like to add a couple of points here, Syed, right? So,
sure.
See, the way I'm looking at it right now is while people are talking about quantum computing, and if you look at some of the market research, that is the exponential growing market for the next 10 years. Communication actually, because the sensors in quantum space were pretty seasoned, I would say, in terms of like photonic sensors and stuff like that. That market is growing at a linear space, and the mid tier of the technologies that will grow in the short span are around quantum communications. Especially in India, I currently see a lot of startup ecosystems mushrooming around the area of QKD, because it looks like a technology where doesn't look like too much capex intensive, and there is lot of hardware integration and the software development that can happen immediately and can be put into production. So purely from this is like a non-Microsoft view, but purely from the way I'm seeing the India ecosystem developing, I think there are a lot of startups that are coming up in QKD. I think there is also a good focus by government institutes on QKD, and I am actually seeing customer traction in the enterprise segment, especially the section which deals with either the financial data or the personal information, PII data as we call it, about looking at what the regulation says versus how the quantum post-quantum cryptography is going to look like, because the threat of exposure is real in this field. Like for example, today if we are projecting that quantum computers at production scale will become reality in say next 6 years, for the financial industry the data protection is required to be guaranteed by for say 15 years, right? That is the RBI guideline. Then if a data is getting compromised today, even if that is not really readable or decryptable by a hacker, even if he is able to store that data for 7-8 years and then sort of work his way through it, a financial institute is still looking at exposure 7 years down the line and protecting that. You don't really have a direct methodology to protect it. There is a massive effort that is consolidated in US at NIST to shortlist and standardize a set of post-quantum protocols. And like cryptography, right, it takes huge amount of time to get a standard mainstream. Like even in the current cryptography standard, whatever is our current cryptography standard, I think only 20% of the enterprises are at that standard, and everybody else is like N-2, N-3. So you know, getting that thing right is very niche area for a lot of regulation governed industries, and they are having a close watch. At the same time, dabbling into small POCs to see if at all a disaster strikes, what is the capability of the institute to switch gears, and then there is lot of consulting space available here in this space to figure out for each organization, can I assess the risk and can I put a dollar value against that, so that companies are aware of the risk that they would be carrying for next 7 to 8 years till the standards are mainstream. That's my 2 cents on communication and cryptography, folks.
Thank you, ma'am. Those were really great insights. I mean, cryptography and QKD indeed, deserves its own session entirely. Okay, before we delve into how microwave is being used in quantum computing, I'd like to touch upon a really hot topic which students are very very curious about, which is careers in quantum computing. I mean, I've had many students, many of my colleagues, and many juniors ask me, "Is there really a PhD required for getting into research roles in quantum computing, or becoming a software or hardware engineer in the field of quantum computing?" Or even a master's degree is required or not. It would be great if you can, touch upon certain points about careers in quantum computing. Shesha sir, would you like to start?
Yeah, IBM recently put out a couple of interesting roadmaps. One was related to the hardware. The other is perhaps more interesting to the question at hand, which is the software roadmap. I think the projection. So basically, the question is, how are we seeing in the years to come the software landscape evolving in the quantum space. So there, essentially, there are three layers coming into play. Now we are getting into a phase where when, say, 5 years before, when IBM put out that machine and then open source things started, and then people started contributing, it was people doing everything. The same set of people, physicists, writing the program, developing things. They were doing the whole gamut of things. But that it has attained certain amount of maturity, but equally at the same point, you require specialized skills now. It's getting to the next level now where you need to have everything can't be done by the same group of physicists all the time. That's not feasible and that's not viable. So the roadmap in terms of software is that you're going to have three layers, at least in the next foreseeable future. One is the what is called as the kernel developers. I'll talk about what each of them are and in their functionality. Next layer would be the algorithm developers, and then the third layer would be the application developers. The kernel developers, they are closest to the hardware, and this necessarily requires some specialized skills. Here, you can imagine somebody with advanced degrees in math or physics who sort of understands how the actual hardware works, whatever be the technology, be able to talk to the technology, tweak with the technology, whatever is the latest that is coming through in the technology, leverage that and develop some sort of a kernel that will do efficiently on that particular hardware or a technology. So that's the job of a kernel developer. They are going to be closest to the technology. Algorithmic person is going to be a little next layer above it. They're going to be little detached from the actual hardware. They're going to work on top of the kernels. So the kernels, once that is abstracts, and you think of it as, say, some sort of subcircuits. You get a set of things to do certain set of compute, right? How do you paste them together? How do you stitch them together efficiently? Here, more likely, you're going to get into the space of engineering, where you're likely to have people with perhaps advanced, perhaps not, it depends. But more likely, you need to have some skills in the computer science space, right? The engineering space, where you know how to stitch these things together in an efficient way. And that's more an algorithm. So you then form a set of algorithms on top of the core kernels that you get out of it. And then finally is the application space. Now, at this point, you have 6 set of algorithms. And then it's about how do I take this algorithm? Which algorithm fits better to the which application space? And some of the applications that Shalaka mentioned, perhaps, right? So those are the kind of applications you're talking about. You're looking out to see in the marketplace what are the applications that would be of relevance. I see this algorithm does this kind of things efficiently. What kind of problem maps into this? Or another way, this is the kind of character of this algorithm. What can I solve with this, right? So you can look at it both ways. Here, you will see a very computer sciencey engineering perspective or an application development perspective coming into play. And that's going to come on top of that. So you're likely to see that what was essentially done by the physicists or advanced mathematicians in the last few things, they're going to now move down to the core layer, the kernel layer, or even some of them maybe in the hardware side, the actual development of the hardware. And then you're going to have the engineering domain slowly creeping into these higher layers and contributing. So that's how it's going to evolve in time. And then you're going to have specialization across each layers, because you need expertise now. We need to now develop expertise. And that would be the need of the hour. And I think that's going to crystallize in time, where the hardware is slowly getting abstracted out and you have very specialized skills, much like the way in the classical side. Very few of you would perhaps know what is the hardware architecture being used in the computer that you're running. You won't even care about VLIW, or if I say RISC architecture, you won't know what that is, because those are all completely abstracted out from you. Then you have your firmware developers, you have OS system person, and then you have compiler optimizers, and then you have your application developers right at Java layer. They don't know anything about what even the operating system would do, right? So all these things are getting abstracted out, and there is specialization at each levels coming in. So I see similar track emerging now, and IBM has put out this roadmap. In the next few years, we're going to likely to see these kind of abstractions coming in, and specialized skills developing across these layers.
I would like to add a couple points and extend more than what Shesha mentioned. Like Shesha mentioned, application developers, right? So that's where I come into picture. Like I was working in Python machine learning, and I was working on Java for cloud computing deployments. So from there, I made a transition to quantum area, right? So here, there are a couple algorithms that I started working with, like quantum SVM algorithms, QSVM. So that actually helped me understand how this QSVM works with quantum kernels, basically. So you can take advantage of quantum kernels, and then you're working with the quantum feature maps there. So that application layer, when you're working with application layer of development, we are already interacting with the algorithmic layer of development, basically. So another application that I would like to mention here is, so let's say feature selection, right? Feature selection is something that isn't available in quantum today, but we know that machine learning algorithms has feature selection. But if we want to explore quantum kernel or quantum feature maps to feature selection, that is possible. And where do we fit into those three layers Shesha mentioned? Is an algorithmic layer. So then we will have to go enter the algorithm, decode what that algorithm is currently doing. I'm just picking the same QSVM algorithm itself because that it works with quantum kernels there, right? So we can change that existing algorithm to what we need. So maybe it is feature selection, or maybe it is regression, right? Anything. I'm just mentioning one of the couple machine learning algorithms that you can start changing into quantum algorithm layer, basically. So the transition from a normal application developer, classical application developer, to quantum application developer, it is possible. And that is possible through exploring more of QSKIT and working with QSKIT tutorials, working with quantum applications there. I mean, they have tutorials which we can explore it into. If you already know ML area, then start applying those to your ML area problems, and there we can actually work on being quantum application developer and also dig deeper into being algorithm developers. Thank you.
Thank you, Kavitha. QSVM is indeed a starting area. I mean, I remember starting out with quantum machine learning with QSVM. You start out with a little bit of quantum computing and machine learning with Python. You just combine them together and you get the QSVM. So you just add the quantum feature maps in the quantum variational circuit, and there you go. Your support vector machine gets converted to quantum support vector machine. It's actually great.
And then the PhD part, right? PhD part is a confusion area. I think even I had masters in University of Washington, and it's been 9 years, and I really wanted to embark PhD then. And I'm like, is it PhD still required to be in quantum area? I think to be an application developer, you don't need a PhD. But if you have PhD in this quantum area, definitely you will be able to solve the algorithm problems much deeper. And because I work with people who have PhD in quantum photonics or quantum superconducting, right? So, I mean, the understanding that they have is much deeper. So it depends. If you want to have PhD, it depends where you want to land, basically. Yeah.
Exactly. So following up on your the three layers which you defined, Shesha sir, like the kernel development, algorithm development, and the application development. So if you talk about specifically the kernel development, so considering this is the MTTS microwave track of IEEE, I mean, what sort of courses do the students have to take up in their masters if they're preferring masters, because that would be required for kernel development at least. And I think it'll be relevant to the students who are attending this session. They're mostly from electronics backgrounds.
Right. I think going broader in terms of compute, superconducting qubit is but one technology. Just to level set it right, there are competing technologies. The current front runners are the superconducting and the ion trap technologies in terms of where the industry is. However, there are other competing technologies. Okay, having said that, the microwaves in the context of superconducting qubit. So let me be more precise on whatever I say is limited to this, because my knowledge of other field is rather limited, and I don't want to broad scope my comment beyond a point here. So in terms of kernel developer, um, uh, an advanced degree would be certainly useful, but by no means it may be necessary per se, but advanced degree would be useful. For example, you do your bachelor's in, say, physics or something, you will get into some amount of things, and if a student is good, they can get into industry and do this job. But by and large, an advanced degree is always better. Now, in that advanced degree, the obvious thing is you'd want to have some basis of quantum physics or quantum mechanics, some understanding of that mechanics and how things work, the rules of the game, etc. Understanding that would be very useful. And then once you have those baselines set, then microwave theory and few of the other things will become more important. If you so note that the kernel developer is just a layer above the hardware, right, where the experimental things. There is sometimes an overlap in a way. If you work in a firm that has a hardware offering also available, then it's a very unique skill set in that optimal control is a difficult problem to do in terms of as the technology scales, how do I manage all the complications that I will have as the scaling happens, and how do I control it optimally, is a sort of a very interesting space and very interesting hard problem to look at. You would need skills from various levels. Control theory would be one aspect, microwave and other knowledge of it would be the other part. And on the implementation side, how do you implement this in actual hardware? Currently, we moved from a standalone separate hardware generating these signals. Eventually it's going to integrate, right? Things are going to move closer, where the signal generation part and the signal consumption part, which is the qubit, can't be very distinct. They'll have to converge at some point. How do you make them work together? These kind of problems are very hard problems to solve, and it requires some skills at various levels. So the kernel developer is in that very interesting space, at least in the current phase of the technology, where if you had certain skills in control theory and, as I mentioned, quantum physics and say math, and plus you have a sense for some sort of electronics and other background, you get into this very interesting space where there is a lot of challenging problems ahead. There will be a lot of interesting work to do. So I would say broadly say these are the broad categories of spaces that you want to be if you're a student and if you're interested in this kind of activities. And there is also many research opportunity in this space naturally, because it's not a solved problem, and it's actually a lot of open problems in this particular space that is very relevant to scale this technology to a level that can solve real problems of interest.
Thank you for the insight, sir. Ricardo, would you like to talk about the different opportunities that you have come across for students, because you're a recent graduate and you'll be able to resonate really well with different research as well as engineering opportunities for students in quantum?
Okay, thank you. I would like to answer the question in student perspective. So sometimes it is very scary to enter a field which is very new. For example, in my country, quantum computing is not yet very well developed, and it is not easy to find mentors that can guide students who are very interested in the field. So in this opportunity, I would like to reassure students to not afraid. So if you are interested and feels excited about this field, then go for it. Uh, I'm speaking from my own experience, and there are not a lot of faculty members in my university that have experience in quantum computing. But one of many things that this community are very good at is the free and online resources that are available across the internet. I mean, there are a lot of very great online courses, tutorials, like Cascade textbooks, for example. And we can also access the IBM's real quantum devices for free. The community also always ready to answer your questions. You can freely join the Slack's community in Qiskit and Sanadu and from others company. There are also a lot of great Discord servers that discuss about these topics. So I believe if you are interested in this topic, even though maybe your background is, let's say, not related to quantum physics, I think it's worth the try. And the barriers is probably there, but I think it is still manageable. And don't let these barriers prevent you from start learning the quantum computing. I think that's what I can say from my past experience.
Thank you, Ricardo. Great points. Arun sir, would you like to touch upon a few quantum opportunities in academia that we have in India right now, or which are going to open in the coming years? Sir, could you please unmute yourself?
Oh, I was speaking, but it is muted. So, yeah. So I would like to say a few things. So in India, if you see over last 10 years, there are many institutes. They have started actually, research group in quantum computing, quantum information. So, for example, at HRI Allahabad, we started this group about 10 years back, and at any given time, you will find about 15 PhD students in this, in our group, and they finish PhD in 4 5 years, and they go for postdoc, and they join some company or they join academia, and that happens. So a lot of opportunity, a lot of openings are there. So if some of young students they want to do PhD, so you should explore these institutes. I mean, in India. So along with this, our HRI, there are groups also in like in SN Bose, also in ISI Calcutta. Also, you'll find people in IISc Bangalore, Institute of Mathematical Science Chennai. So there are many institute. Yeah, of course, Ajir Mohali. You'll find there are many people doing quantum information. So a lot of openings, a lot of opportunities still there in India. And in next 5 years, I think this is even there will be more opportunity, because as you might have heard, government is planning to invest 8,000 crore in this area. So and there is also proposal to have an institute of quantum computing, not computing, I mean institute of quantum technology. So they want to train the PhD students at least every year. They plan to take about 30 to 40 or maybe 50 students every year. So that is the future plan. So I think there is a lot of opportunity in future. Yes. Yeah.
Thank you,
Well, I'll
sir.
just add to that
Yeah,
in
sure.
terms of so in the context of in the Indian context now in particular, we know that the broader IT space, where IT services and that space, India is a big player in the world market, and I think in general something in the order of according to government figures, we are looking at $170+ billion of revenue coming through from that particular activity, and something in the order of, if I remember correctly, 4 to 5 million people are involved primarily or tertiarily on this business. The number of people working, I'm not sure exactly whether they are directly or maybe there is a second level, third level type engagement or not, but be that as it may. So as the quantum space evolves, and the direction seems to be very positive in the last few years, and if you project that further out a little bit, in 3 to 4 years time, when the hardware is at a point where it can solve some interesting problem of interest at scale, then you are looking at potentially productizing this. What that means is that then as time progresses post a production, right, you will have an industry building around that. You will have a space building around that, how to deal with those things. Let's just go back to 10 years, right, when GPUs first came into the marketplace and machine learning was still new as a programming paradigm. So when the hardware came, then you have the whole ecosystem evolving around that hardware, and then you have many opportunities, starting with the startups, and then you have building it into big enterprises, and then everybody adopting it in a broad scale. You have a sort of there is a full wave of things that happen. So when that happens, you need people to program these devices. You need skill set at various levels.
Yeah, completely. Yeah.
Right. So which means that if you have this skill set as part of, say you join a undergrad course this year, and by the time you graduate in 4 years time, let's say the hardware is at a point where it's fairly mature, and there are some solutions coming into the marketplace, right? If you have the skill set in this space, even in the undergrad kind of a background, right, then slowly opportunity is going to open up. At that point, you would need that skill in the marketplace. And if you see the projection from, say, BCG and others, they are projecting in the order of $2 to $5 billion as the kind of number they are saying by 2024-ish timeframe. By the end of the decade, they are projecting something in the order of $50 billion plus as the potential market, and eventually it's going to go close to 500 to 700 billion. Those are all further out projection. But if you see through this decade, you're looking at a marketplace of 4 to 5 in the next 2-3 years time, and then eventually by the end of the decade something in the order of $50 billion. Then you're seeing a market, then you're seeing an industry building around it, which means you need to have skills in that industry, and that skills would require you to know some of these aspects based on your skill set, different levels that I was talking to about earlier. You If you graduate with appropriate skill set, and the industry, the way it's maturing along the way, you're likely to be at a good place to leverage your
Yeah,
skill
definitely. I
in the
mean
industry.
that should be the ultimate aim, and there should be, as you said, there should be ecosystem between industry and academia working in India or working within Indian institutes. So I think there is a plan from government side to have that kind of collaboration and kind of um, sharing of knowledge, sharing of exchange of expertise, and so on. So that will happen. I mean, next 3 to 5 years. But maybe since already you are working in IBM, I don't know whether IBM is planning to do something in India on hardware side. Do you have any idea, any plan or any idea?
Um, in the hardware side, I'm not sure, but
Mm-hmm.
currently I think our interest is more on the software side. So it could,
Software side, yeah.
the three layers that we talked about, it
Mm-hmm.
could span those three layers, because
Mm-hmm.
if we are at the research level, we probably will be on the lower level of the layers, and if we are on the application level, we will be on the higher level of that thing. We probably will have much wider coverage on the software stack, at least in the immediate future. I think that's probably where our play will be in the immediate future.
Mm-hmm.
And a
But
point to add to
hmm,
that, right? IBM has a IBM Quantum Network where it's a community of Fortune 500 companies, academic institutions, startups, and research labs working with IBM to advance their quantum computing skills. So it's in this there are also industries actually trying to do research in quantum, and they want to have their presence in quantum computing today. So maybe in a couple years down the line, when there are more qubits and they can solve their industry problems, so they can really solve their industry problems and have a the way Sesha mentioned, it can be a product for the company. But now they are into initial incubation state with IBM Quantum Network today.
mhm. Mm.
Thank you
But,
for
but,
the
but
insights.
yeah, but at some point, IBM, if they can somehow start a, I don't know, research center with all the even hardware development, that may benefit India, because you see, you have to train young people, they don't have that many expertise in hardware, even though I have been working for more than 30 years, but I do mostly theory, you see. So there are people doing theory for more than 10 years, 20 years, in India, but on experimental side, on hardware side, we don't have that many expertise. So if IBM can bring some of their expertise to India and start a center, and then we hire young people and try to train them, and then slowly we build up the ecosystem. That will boost up the thing to a large extent. This is my feeling. I don't know. So, Shalaka, you want to comment something on this?
No, so I'm just going to give you a industry perspective, and I'm just going to speak on behalf of a lot of big techs here, Arun, right? So, most of the big techs who are active in quantum research, we all know that this fundamentally is a capex intensive field, right? And so people like to have those kind of capex intensive investments localized. This is how, if you remember, the semiconductor industry evolved. We never had the VLSI lithography plants coming up in India because of the downstream and upstream supply chain, right? If you really need lot of moving parts, then you will have a problem. So there was, I think, a concentrated effort done by Government of India, Government of Telangana to be very precise, to create that upstream and downstream, and then that turned out to be a humongous task. So, I see a lot of big techs doing their capex intensive investments in the research in their top research centers. And for now, for IBM as well as for Microsoft, those centers seem to be based out in US. There is also significant expansion I see happening in China by nature of the demography itself, and also in Japan because the pull is there. But other than that, I don't see a lot of diversification. While I stay with that thought process, what I'm seeing happening in India are two major strategic shifts, right? One is the government of India announcing $1 billion into the quantum computing space in next 5 to 8 years. I'm sure that some of that money will start getting assigned to some of the projects which are capex intensive, and then it is for want of entrepreneurs to come up and pick it up. And I think there were few people, there are a lot of people sitting in the IITs and stuff like that who have got good experience, at least at a ground level, to develop smaller systems, right? So it's a matter of time if they are able to receive that kind of fund, prepare a project plan and move that forward. And if that starts happening and the ecosystem starts blooming, I think there would be a lot of consolidation that can happen. But given the population in India and given the fact that we are a young country with a lot of engineers coming in, I think a lot of effort will get focused on the development ecosystem in the software space, which is not very capex intensive, but at the same time it can create a good ROI in a shorter future, right? So I think that is where most of the effort will go, and this is where you will see a lot of big techs consolidating. Because they can tap the potential both for their downstreams. Like for example, if I'm looking at Microsoft, Microsoft's business model is to change the enterprise, transform the enterprise via the partner ecosystem. So effectively, if tomorrow you want a quantum application to get built, while Microsoft Research will focus on the backend, and on Azure Quantum you will get access to the third party hardware. Today you have got like what, IonQ, OneQubit, Honeywell, all of that is accessible on Azure Quantum platform. But what you need is an enriched layer of the algorithm and a rich language. So there is Q Sharp, there is QDK, there are katas which has got a rich set of algorithms. And now for making this real to the customers, Microsoft will not have that kind of soldier army to really reach out. So effectively it has to be via the partner ecosystem. And if you look at the partner ecosystem, the big SIs who will drive the innovation are based, their development for hubs are based in India, and the largest mushrooming startup and unicorn ecosystem is in India. So the most innovation on the application tier will come out of India, and that is where you will see the shift and the investment in terms of skill build.
Yeah.
And also on the experiment question, so one thing to note is that quantum technologies are closely held. There are export control and other regulations that kick in with those kind of technologies, particularly at the core hardware level. Some of these are probably beyond even me or any of us within this space. It has to happen at much higher level, if at all. I think there will be opportunities for, say, students to do internship, etc. But again, there are a few things that have to happen beyond. We can't say never type thing in that it can happen in the future, but there are many other layers when it comes to the actual hardware being deployed and experimental things being done because of some of the other things that are beyond just any of us here.
Thank you for the great points. I'd like to take this chance to talk about the entrepreneurial support which is available in India, especially in the US and UK. We have a lot of venture capital coming in into the startup ecosystem, especially in the quantum space. So, where do you see this culture coming into India, and does it really require the support from the government, or it can be self-sustained? Shalaka ma'am, would you like to go ahead?
Yeah, sure. So let me try and address this. Like, I think that there is a want for lot more to happen in the startup space in India. Right? We are, I think most of the startups that get started out today are more like family money, angel investors, my good friends kind of situation. Till they enter really into uh, the first round of actual funding, right? And that's really a hard work, especially for people in India who do not have other means of sustenance. I think it can become a hard call, and lot of ideas really die down at that stage. And I think we really need to do a lot in that space. I think that understanding is creeping up. I mean, I recently was reading one of the reports for which was published actually by Gartner on the 5 trillion economy that is vision for this government in India by 2025. And there are sectors that are nominated there, like for example fintech has 65 million, followed by I think the energy sector at about 55 billion dollars, right? And lot of that innovation is really mapped out to be done by the startup ecosystem, because it has to happen at the grassroots level. And I think the big techs and the large enterprises are really having that thought process in their mind when they engage in India now. So you see more mature startup programs, like for example, just to contextualize it in terms of Azure Quantum. If you are a startup in India on a quantum space and have something to demonstrate in Azure Quantum, you can reach out to Microsoft team. There is a recruit motion for the startup team which happens, and they can sort of evaluate you and make you part of the Microsoft partner network, which can give you a lot of options around GTM, some support with the backend development team to really go mainstream and develop application, etc. There are also something like SI engagement programs that the Microsoft is launching. So if you are a system integrator who knows industry very deeply and know how to integrate a particular POC in a customer's environment, there is a lot of support that can come to you from the backend team in the engineering side, etc. Right? So I see that people are trying to do a lot of handholding from the tech side. The government structure and the venture funding structure needs to be there. But like I am part of my many WhatsApp groups right now, which are like trying to create these small impromptu funds to fund these startups till they get into their round one, and I see a lot of amazing products there, right? So I think even the professionals or I would say high net worth individuals in India who are tech savvy are also really realizing that there is a need for nurturing that ecosystem that is mushrooming, I think, almost everywhere. And I have actually seen this getting accelerated within COVID time frame, where lot of people shifted back from US, etc., started something, spin off something from their remote locations, from their hometowns. And I think the cloud economy is really making the barriers smaller and smaller. So you know you are not really now too much dependent on lot of capex to get started. And I'm hoping this will continue, and in next 4-5 years we should be a very mature economy to support the entrepreneurs and startups folks.
Just to add to that, I think the point that she made about the larger big tech, right? If you see, many big techs are investing in startups too. One is facilitating startups, onboarding them, and helping them in making progress, etc. Like Kavitha was talking about quantum network, IBM quantum network as a platform to get engaged, etc. There are many startups there. Equally, you will also see that IBM has invested in some bunch of startups. Now, this comment is a broader worldwide comment, mostly startups in the US, Canada, because they started off first. But as such, you can see that they have started investing in things and ideas that they see potential in, and started investing along with onboarding part of it. That is how to get them going, streamline the process so that they can get access to the hardware that is needed, etc. In the Indian context, I think one other thing that will be interesting to watch is in the broader how the broader deep tech startups come about in India and how they become bigger. And this is a broader deep tech, not necessarily quantum per se. We would want to see more of that coming through. Say Singapore has made a lot of investment over a long period of time to do deep tech startups, and they have structural institutional framework to help them come through, walk them through, and then government supports them to build those things, etc. And then you have VC and other things coming in. They have certain model, but in India we need to see in the general broader deep tech space, do we have unicorns coming through, and do they solve problem at scale, not necessarily in quantum computing, which is a subset of it, but in the broader deep tech. Then that will be an interesting space where you have highly deep tech basically means you have a significant skill getting into solving a problem, and significant domain knowledge, deeper domain knowledge to solve certain set of problems. That kind of space, and if we start seeing more and more of those things emerging, in time you will also have it's sort of chicken and egg in a way. You will also have venture capital funds that are focused on deep tech type thing coming in a big way and investing. I think there are some aspects starting. We'd want to see, it would be interesting to see in the next coming years how deep tech as a broader thing evolves in India, and quantum within that, how that goes through in the time to come. And then you will have the ecosystem like VCs or any other institutional framework that sits on around it, how that helps develop this deep tech framework or deep tech startups. That will be an interesting evolution to watch. Hope it gains momentum. Hope there is more and more of that coming through, so that these are the real value creation that brings more and more money into the economy and the system, and then very high skilled jobs, which means you have high paid jobs also coming in into the system.
Thank you. Entrepreneurship is these are very interesting times for an entrepreneurial career in quantum space, especially when we get support from big companies like IBM and Microsoft. Of course, the entire thing has been accelerated by the COVID times as well. So, talking about microwaves in quantum computing, so we know that there are several platforms that you can use for actually creating quantum computers, creating quantum chips, which can either be using trapped ion systems or with quantum dots or nitrogen vacancies and diamonds. But the most common and the most famous one is the superconducting qubits. So, Shesha sir, if you would like to, talk about briefly what are the things involved in a superconducting qubit and how is it operated using microwave pulses, it would be really good for a electronics enthusiast who have joined this call.
Right. So the superconducting qubit, at a broad conceptual level, is, I mean, it's an artificial atom essentially. What you do is that you leverage a superconducting element, which is anharmonic. Essentially what that does is you're creating an artificial atom with various energy levels. What you're doing is you use the lower two energy levels as a qubit, and the higher energy levels is something that you don't use. As part of that, in the superconducting qubit, you use the microwave pulses to talk to those qubits, because you need to have a way to communicate, and that is through the light. You shine microwave pulse on those particular qubit. If you do it for certain duration with certain amplitude, you can take the system from 0 to 1 and 1 to 0, or any other intermediate state, or like a superposition state, etc., through this. And then you have a different kind of frequency that you shine light at. Then you have channel that connects the two qubits, that then gets triggered based on the detuning, the energy level and detuning, that can connect, and therefore creates an conditional operation on the second qubit, and that's how this two qubit system operates. And the measurement is again the same microwave pulse that is shined, and then you get the wave back at a different frequency. If it is a 0, you get at certain frequency, and if it is a 1, you get it at some other frequency. You resolve the frequency to know whether the value was a 0 or a 1. So that's how the system works at a very simple level. The challenge, of course, in the current era is that the noise. We currently, all these operations, they are very, very sensitive to noise, and the quantum system is in general, very sensitive to noise. What that means is that the amount of time that quantum effects live in the hardware is determined by how noisy or less noisy the system is. In the case of superconducting qubit, they operate at a very low temperature in the order of 15 millikelvins, which is really, really, really cool. That's just to cut down on all the noise effects that can potentially happen. Just to keep that as this thing, or else the thermal energy of the system itself will break things down and you won't get any quantum effect. So you operate at that temperature so that the quantum effects reside for a longer time. The challenge with the current technology is that the more time it is available, the better it is, because you can do more operations. Think of it as the time is there. If you, for example, the current technology, we are looking at something in the order of 100 microseconds as the life cycle of a qubit, and the frequency of operation of an individual gate in superconducting qubit is in the order of 5 gigahertz. So it takes about, for a single qubit operation, something in the order of 10 nanoseconds or so to do a gate operation. For a 2 qubit operation like a C0, it may take in the order of 100 nanoseconds to do. So given that if you have 100 microseconds, you can sort of see how much gates you can do in that space. You would want to increase, of course, the time, the duration where the life of the qubit is much longer, as well as the quality of the operation. So on both fronts, there is a challenge, and there the source of noise could be various, and that's the challenging part in the current technology, in the current era, where the systems are noisy. The quantum computing, in a broader sense, in a fault tolerant sense, will work only if the error thresholds are less than certain very small number. We are little far from that, and that may take a few years to get there. But in the meantime, the hardware itself is evolving in a way, and the interesting part is, how do we cut down on the noise? How do we increase the life cycle of the quantum coherence, as they call it, the coherence time? And through that, can we solve any real world point problem of interest that can be of interest to the broader society? And that's where some of the things that Shalaka mentioned earlier comes in. That is, there are certain point problems of interest that may come in handy, because they may be solvable if the quantum coherence is sufficiently large enough. We think that something in the order of we have a metric called quantum volume. Doesn't matter what that is as a definition, but think of it as one metric like a flop or something in the supercomputer measurement, right? Some measure to say what is the quality of your hardware in some sense, in a systemic sense. So if it goes beyond certain number, we think the horsepower is sufficient to solve some real problem at scale. And that problem can come about in 3 years-ish time frame, where the noise is reasonably contained, which means that I have a lot more time to do my operations, which means I could do a lot more operations, and therefore gives me more opportunity potential opportunity to solve some problem at scale. So that's the broad contour of the challenge in the hardware, particularly in the superconducting qubit, and how to deal with this challenge, improve the fidelity of individual gate, particularly the 2-qubit gate. The challenging parts are the 2-qubit part, the measurement part, and since you have these channels connected together, the coupling noise. Those are the challenging parts at this time to cut through.
Thank you, sir. I mean, it really helped me also to revise all the concepts of engineering with superconducting qubits. Okay, so talking about research going on with qubits, wherein the transition frequency is limited to only 0 and 1 states, but we do have Q traits as well, right? Wherein you do not limit the transition frequencies between two states, but also let the state of the two vector be open. So, what is your take on research with Q traits?
Is it to me?
Yes, sir. Yes, sir, if you can.
Okay. See, the challenge will be if you see the frequency difference, the 0 ground state, the first state, and the second state, right? The frequency is not equally spaced. So what's going to happen is that the ground to the first state is in the order of 5 gigahertz is the frequency, right? And then the first to the second is like 0.3 gigahertz or something like that, right? It cuts down. And if you go to further higher states, it's going to get narrower and narrower and narrower. So why do I say that? What that means is that your control system becomes complicated. If I do not have sufficient leeway to play with, handling all this becomes a problematic thing. So you can also ask the same question on the classical side, right? So why did not have an analog computer rather than a digital computer? Why do we still stick with 0 and 1 and not have an analog? I mean, computational theory wise, it's the same. It would computationally solve the same problem. But in a real implementation science, there is a world of difference. The problem with the analog computer is that control mechanics become so hard to differentiate between 0.6 volts and 0.7 volts. How much of hardware do you put to figure that difference out, right? It becomes harder and harder if you have to scale it to billion transistors, right? It just becomes harder and harder. Q traits, since you asked limited to Q traits, we need to see. It really depends on the implementation. It really depends on what is the cost versus what is the benefit it can provide. There are some possibly values add that it can provide, but what is the cost at which it provides that? What is the control cost for me to be able to manage that, differentiate that? If I have to be able to differentiate the levels, right? And given these kind of things, what do I put it in hardware so as to differentiate this? How do I make it work? How will it scale if I go to 100 qubits? What is the cost on managing all of this? And what is the, more importantly, cost in terms of noise? How much noise would it add if I have to do that in the hardware, right? Because such as the quality of things such as it is right now, it's still noisy. If I do something that has to do more work to differentiate things, I'm likely to introduce more noise in the process of doing it too. So it will be a trade-off to see, but right now, my personal opinion is it may not fly given the noise profile that we are seeing currently, even with just the 2-qubit. And how do we handle all of that, and what is the cost on noise becomes more a primary criteria than others. That's just my personal opinion. We need to see how the technology evolves.
Thank you, sir. Okay, so you've already explained what are the different roadblocks that we face ahead, or what are the different challenges that we face with superconducting qubits, like the decoherence time has to, the decoherence times and different other factors that have to be taken into account. But now I'd like to talk about what are the different barriers that hinder the growth of quantum computing in terms of workforce development, or in terms of formation of communities, or different factors that are involved, which I have not mentioned here. So, Shalaka ma'am, would you like to take this?
My voice was a little bit jittery. Can you repeat the question, please, Syed?
Yeah. So, I want to talk about the barriers that hinder, the growth of quantum computing, specifically in terms of workforce development or formation of communities, etc. in India and abroad?
Yeah, I mean, I won't call this as an hindrance, right? It is like, I would say we are early in the timeline. Like, for example, we did see good community support building in for data science. We have seen, we have a very good ecosystem around developers in India. We do have good ecosystem coming up around different new age programming languages and techniques, the containerization. So I think it's about the maturity. You will see the innovation and the ecosystems developing first at the top takers, right? So like the questions to answer is, does Microsoft have an ecosystem around quantum computing which is internal to Microsoft even for at this stage, where people do not have this as their core job? And the answer is we are just starting. Similarly, does a company, a large SI in India, even though there are not too many mainstream jobs today on the quantum computing, do they have an ecosystem coming up? In my experience, they are starting out. So, there is still little bit amount of time for us to have a structured community buildup. What we can do now is to start small in a very specific environment. Like, for example, a large IIT, can they look at a quantum computing program for faculty, for a set of students, for PhDs, and so on and so forth. Similarly, can a government ecosystem can look at creating a niche industry excellence domain and can have a set of developers plugged in there as a community, right? I think we are at that stage and it's happening. I really don't see hindrance in terms of democratization of knowledge in quantum technology. I think it's the need of the hour. People are pushing for it. Lot of education available online. I think at some times there is also an information overload. So, having the right kind of mentors and people to guide you on how to smartly invest your time and navigate your career is important. But for the larger students community, my 2 cents would be to touch it on from a long-term basis, right? Because tactically you will always overestimate what is going to happen in 3-4 years, and strategically you will always underestimate. But you starting as a new professional in the industry have a long career span, and that career span is not necessarily into research or into engineering, right? If you look at the industry adoption of a technology, then there is consulting, there is sales, there is marketing, there is finance, there is business support, product management, then research, development, ecosystem build up. So, think about myriads of roles that are going to get available eventually, and all of you will have that career span to land in one of that area. So think about, pick up a field. You can start with something else today, but you may have a vision on how that eventually connects into the larger world of quantum computing. The learning needs to be more like tree, folks. You go deep in a set of domain that can be very specific. You can be a good banking consultant. You can be a banker yourself, or you can be a very good healthcare industry consultant, and then start touching upon the technologies which sort of have this. I would, for want of better word, I would call it as generalist, right? So you have a deep knowledge in a domain, and then you expand into a set of technologies which sort of connect into that particular domain into various professional streams, and then you take your bet on which side of the industry, which side of the profession is something that is closer, that you harmonize with, and then take up a learning path around that area, and then just keep going forward. And I think the dots will always connect in the hindsight. Do not bank too much about starting a quantum computing career today. because then you are really looking at core development and core engineering and core research jobs that are going to be very real in India. But think broader term.
Thank you, ma'am. Thanks a lot.
So in the short term, though, Farhan, I'll just add one piece there. Since as part of my ambassador work, I do engage with students regularly. Um, there is a lot of groundswell of interest among students in this technology. I see a lot of interest to get into this space and want to learn this space. The In the short term, what Shalaka said is really true. But in the short term, my comments are limited to the short term. I think where I would call it hindrance, but I will say there is a gap. Where there is a gap is the skill development part. Avenues to properly hone the skill. I think there is also a lot of push from the academia and everybody I talk to want to have a structured course around this field, so that there is at least some course offered even at undergrad level that teaches some elements of how to understand this field, how to program, etc. I think there is given that there is both push and pull in terms of the academic institutions. Here I mean engineering colleges, not high-level research institutes per se. Um, Wanting to be able to offer some courses in this space, and also there is a groundswell of interest from the students to go learn this space. It's matter of time when you will have courses as part of the regular engineering that will start teaching this in a more structured way, so that in the coming generation, the next wave of students will have gone through a proper coursework along the way in terms of learning about this technology and so forth, and be ready when opportunities arise.
I want to add 2 points to what Sesha mentioned. That's opportunities to students, right? Um, Quantum developer certification is just released a week ago, not even a week actually. So there are several levels of certifications in that: L1, L2, L3. Right now, it is the foundation level certification that's been out there, and there is no end date for that. So, what I mean by this is, if you actually read qskit.org and qski.org and then prepare for the first 4 or 5 chapters, you should be able to clear the level 1 or foundation certifications. And then students out there with this foundation certification can also try to become qskit advocate by doing contributions and such. And the software layer that we were talking earlier, students can even enter there. So these are my 2 points I wanted to add to extend what Shesha was mentioning. Thanks.
So, by the way, if students are interested, I mean, after doing BTech, so recently, Indian Institute of Science, they started this MTech program in quantum technology. Some of you might have already know this, but if you don't know, maybe you can look at their website, and I think it is still open. So, and not only that, there is a Defense Institute in Pune. I forgot exact name. So they also have MTech program in quantum technology for last 1 year. So one of my friend he joined there as a head of the school of that program. So he was telling me that they started this MTech program. So I think slowly many engineering college and technology oriented centers also starting this MTech program in quantum technology. So it is useful for students. Yeah.
Yeah, and also just FYI, many research institutes also who traditionally offer quantum information course, which is highly very theoretical oriented courses. I mean, like 15, 20 years, say they've been offering these courses, are now reorienting this coursework towards more how do you bring in lab content into the coursework? How do you look at more later modern algorithms that are coming through, that are more tuned to the hardware requirements of the current era, and the noisy systems that are available. So I sort of see a lot of interest even in the advanced research institutes to tune their coursework and realign that, because the theory part, the quantum information science, has been there for some time. It's the last 5-8 years where the current new algorithms to tune, have it work in the real hardware,
Yeah, that is what's happening.
have
Yes. Yeah.
and there is a lot of push in the research institute to change the traditional way of teaching to lab oriented, even at graduate postgraduate level, uh,
Yeah.
that we need to have some lab content so that students are exposed to the challenges of the current hardware. How do you program them, how do you deal with them, what are the challenges, and that therefore also open up research opportunities in within that space. So there is, along with course offering at the undergrad level, there is research level tuning of the coursework happening, where everybody wants to say rework the keep the theory part, but sort of work it out in a way that you fit in the lab portion in, so that there is a more complete experience to the students going through the coursework, and to get a feel for what it is to actually run things in actual hardware and see it work.
Yeah, that is a very good suggestion. Yes. Yeah.
Thank you, sir. Uh, I'd like to talk about where do we see this quantum technology going in the next 5 to 10 years? I mean, 5 years and 10 years to be specific, because a lot can happen in the next 5 plus 5 years, right? So, uh, anyone would like to take it up?
Yeah. I mean, there is no doubt that next 5 years we will see a huge progress, tremendous progress, at least in trying to scale up the number of qubits. So currently, Google has uh, 65 qubits and so on. So IBM is planning to uh, increase the number of qubits in the processor. So that will certainly happen. But we don't know whether 5 years is enough to really have a quantum computer which is capable of doing error correction. So for that we need at least million qubits, uh, which is a great challenge. So that may happen in next, I don't know, maybe 15-20 years. So but this intermediate, so-called this noisy intermediate scale quantum computer and this quantum computer, that may be able to scale up to some extent. So and maybe companies and industries, they will use, as Shalaka was trying to mention, that you can find some application, useful application in finance or maybe in chemistry or maybe simulation of complex physical systems and so on. So those kind of applications will take a, will make certain great progress. So that is my feeling. So
Yeah, so I think perspective, at least that IBM has, is that in the next 3 to 5 years, we should see some breakthrough application coming through, which is an important fillip. You need that kind of demonstrable capability that it's providing a value beyond what can be done, a demonstrable advantage over what is currently doable. That will be a very important milestone in terms of a problem at scale, a real problem at scale. I think that will be the next big thing to look for in the next 3-5 years. Hope is that we will have at least one or two of them coming through. The likelihood of that is more likely to be in the quantum simulation space, uh, less on the more advanced other technologies. It's just a probability thing. The odds of finding a solution that can provide value in the simulation space is higher than doing something more advanced in, say, quantum machine learning or any of the other. First, I think this is probably the first wave that's likely to come, and then you're going to have next set of waves coming through. Once that demonstration happens, then it will have a whole ecosystem developing around it, and then you're going to have further waves where more advanced capabilities will be demonstrated at scale. So 5 years, I think, is probably the farthest you want to look at this time. So there, some problem at scale, more likely simulation problem, is demonstrably shown to be better solved using quantum than in any classical hardware. that would be something that is worth cherishing. I mean, if that happens, and as and when that happens, that will be a real boost to this technology, and also this will then take into a different scale once that is shown.
One more example to what was 2 years ago to what is now, which will help us actually think what would be the future also, right? For example, we know the support vector machine can actually simulate a lot of features, right, in machine learning. Coming to QSVM, quantum support vector machines, that algorithm, at least 2 years ago, I was able to simulate only like 3 features. So today, we are able to do 30 features. So it is 10x of improvements, like 3 features to 30 features. We are able to simulate that many features today. So, I mean, I have not checked more than 30 features, but 30 features was the benchmark I was working on, and then what it did. So basically, what I'm trying to say here is, if we can actually do this 10x of improvements every year in the number of simulation of feature simulation, then it's the quantum supremacy. It's not just the classical problems. We are not trying to solve the classical problems in quantum, but what is not solvable in classical machine is something quantum supremacy is going to come into picture. And I think it's going to be huge, and we can see the results in even the routing problem, right? The quantum optimization, Shalka was mentioning, optimization. You can group several problems into optimization, and then routing problem is a NP-hard problem, and then that is also another optimization, even portfolio optimization. So today we are able to simulate, or 2 years or 1.5 years ago, we were able to simulate only like 4 or 5 cities or 4 or 5 cards. Today we are able to simulate even more. So the future is definitely there on the roadmap of IBM roadmap, and also we're able to see results from last year to this year, which is a bit huge.
Thank you, Kavitha ma'am. I've always
So
wanted to know about. Yeah, go ahead, ma'am.
yeah, yeah, sir. No, just couple of points, right,
Sure.
folks. So uh, what I feel that the way I see enterprises looking at the adoption on quantum computing, and what I'm seeing on the ground, right? So there is this huge affinity towards solving the optimization problems. Now, the optimization problem has got two legs to that, right? One is improving the efficiency at the algorithmic level, and then actually getting the benefit out of quantum computers. And if you look at companies like Toshiba, One Qubit, even to that extent, some of the algorithms released by Xanadu and Dewey, right? Most of them are focused on the algorithmic improvement in the classical optimization space itself. That is not really dependent on any quantum hardware in the backend, right? So same is on the QIO, which is called as quantum inspired optimizers on Azure Quantum. And by the way, on Azure Quantum, you get access to all other optimizers that I was talking about. So this approach is very different, and it is decoupled from the actual development in the quantum hardware space. And the fundamental thought process here is, because the quantum hardware was getting developed, people started thinking about solving some of the problems in a very different way, and that algorithmic improvement itself is a big deal in some of the industries, like power grid management, like route optimizations, right? And you don't really need quantum computers for it. So the case is really about learning from quantum hardware, creating an algorithm which can run on a simulator and still give you an advantage, either in terms of time or in terms of accuracy. And I think this is something that can really get mainstream in a short time. Next 3 years, 4 years, it's a matter of going deep into an industry, developing a business case, figuring out. I mean, at the end of the day, a company will pay money for solving a problem, either if it either helps them earn more money, or saves something for them, or it solves a problem that is unsolved for the industry, and there is a huge barrier to copy the step for an enterprise. So really create an IP for that particular business. So any three of these things you are able to nail in terms of a use case, you will see an investment in an optimization problem on a simulator space. That's my take in the short term. The hardware space actually is a little bit farther ahead in terms of roadmap. But what we are trying to do, especially at Microsoft and Azure Quantum, is create this volume and score based resource estimator, right? So for example, if you really have an industry problem which is circuit driven, then you can get that algorithm and run it on a resource estimator, and it will tell you for existing hardware complexity, right? So like for example, on an Honeywell kind of qubit, for your scale of the problem, what is the number of qubits that you will need to really go in the production? And then you can say, what if I reduce the problem size? What if I reduce the problem size? And by the way, there are some startups that I have seen doing an phenomenally innovative work in that space, and they are saying, okay, if my scale is going to get restricted to equivalent of say 27 qubits in next 3 years, then can I break my problem in a way where I can repetitively run with 27 qubits and still get an accuracy? Probably I'm going to take more time, but can I get an accuracy which is very lucrative for a business? Like for example, say a portfolio optimization for a bank. They are not going to change their portfolio every day, maybe once a month. So an algorithm that is solving it in 7 days versus something solving it in 10 days, it's not a big deal. But if that is going to result in 5% of additional money for the bank, huge deal, right? So there are people who are taking that approach, living with the fact that the machines may remain smaller, but there may be a different way to sort of address the problem in a different way, breaking it down in a different way. So I think there is this lot of IP buildup that is happening in terms of how you innovate around the innovations that the ecosystem will, or the constraint that the ecosystem will provide. And I'm very hopeful that some of that stuff will come really through in next 4-5 years, folks.
Thank you for the wonderful insights, ma'am. Okay. Before we take questions from the audience, I'd like to touch upon one of the most popular topics, that is quantum machine learning. Well, Kavitha ma'am was talking about quantum support vector machines. Well, we do have quantum assisted AI, and we have AI assisted quantum. AI assisted quantum is where you use artificial intelligence for error mitigation techniques in quantum computers, or if you have quantum assisted AI, then you're using hybrid quantum classical algorithms to solve the machine learning problems that exist today. So it would be great if one of you can touch upon a few of the applications of hybrid quantum classical architectures, or any of the quantum machine learning applications that could be possible in the next 2 to 3 years.
So I'll take the second part, which is quantum AI assisting quantum part. So the challenge with the current hardware is how do I maximize the so there are some constraints that we currently have. So we have the finite time for which the quantumness lives, right? And I also have the qubits that are built, the topology of the qubit that is available, and no two qubits are equal in terms of its error profile, etc. So the challenging part is how do I take a particular problem, whatever that I want to implement, how do I maximize the capability of the hardware in terms of naturally reducing the amount of noise that I will hit, or alternatively, how do I improve the probability of success of a particular algorithm? There, in a way, it is an optimization problem. In a way, you can also see it as a machine learning problem too. Given that you can think of various techniques, there have been approaches to look at the hardware and develop a model that will sort of predict what is the likelihood of error and what is the amount of error, and therefore can we do something different in terms of mapping problems. So how do I compile it into hardware and run it? What would be the techniques? There, some of the machine learning things can plug in. There are some works around that. So here what we are trying to do is you have the hardware, you have the high level program. How do I run it in hardware? There, some aspect of it is leveraging machine learning. There are explorations around that, and therefore you can potentially see some benefit by leveraging some of the advantages that machine learning may have. And you can potentially look at having models per hardware, perhaps. As it goes through the stream, you sort of tune the thing so that you get a better result out of the system. The other thing is that the hardware also, the errors also are not fixed or not constant. In time also they change, they can move up and down, and you can tune the algorithm. The machine learning thing can be sensitive to that, and therefore it could do a better job of taking the high level program and transpiling it into hardware a little bit more efficiently, and perhaps do something smart. And one of the papers was about padding, and identifying padding, and using machine learning to do some sort of prediction and include padding based on that. So there are some aspects that are they are trying to solve some specific point problems there, where machine learning is leveraged to solve the particular problem. Having said all that, currently it is still an evolving space. Whether all of that will scale up to a full-fledged algorithm at production quality at some point in time or not remains to be seen. But there is a lot of interest in exploring, can machine learning solve some problems in the quantum space, so that it increases the probability of success of the algorithm by perhaps working out the order of execution the right way, and predicting what is the likely error. Perhaps I map this logical qubit to a different qubit at some point in time. Maybe that gives a better result. So those kind of things are being looked at. There could be many more advantages going ahead in terms of problems that are being looked at, but these are some of the recent works that I've seen where AI is being used to solve this broader quantum problem.
Thank you, sir. Uh, Kavitha, ma'am, would you like to touch upon some applications of quantum machine learning?
Um, sure. So today, with the limitations of qubits, right, I would like to start with that. And yeah, we are able to produce some applications from classical ML to quantum ML, definitely, but the qubit limitation is something which is still not giving us the complete advantage of quantum machines today. We are able to use quantum kernel space and use couple features like Z feature map or ZZ feature map, using different types of entanglement, and trying to make sure we leverage all the all the Hilbert space over there, but with one qubit we can say one feature with QSVM, one example actually. And then we have IBM Quantum, the IBM Q Manhattan is about 65 qubit machine. So does it mean that we can do 65 features right away on QSVM using IBM Quantum Machine, the real quantum machine there on the cloud? Probably no, because of the noise which is actually right there, the noise mitigation or error mitigation that we will have to handle. But when we are dealing with simulators like state vector simulator or a quantum simulator using QSCAT, the 32 qubit simulation is something what we can do, and which is noise free and error free. So with this, where I'm coming to is the applications of quantum, right? So can quantum do classification better than classical? Probably not today, right? Not right now, but with quantum we can do classification. How we can do, we can take the advantages of quantum kernel space and try to do classification over that, which means we are converting a problem into a non-linear problem and putting it in kernel space. And when we have more qubits, the idea is this: when we have a lot more qubits, we will be able to simulate more features in quantum than classical feature simulation. So that means that we can do more classification in QML than in the classical ML. So this is something that I can say with classical ML and quantum ML. And other areas, right? Earlier we had classical neural networks, now we have quantum neural networks. So there are algorithms which are coming up day in and day out. And HHL algorithm, which is basically trying to take the matrix inverse. So that we can do with quantum today, with quantum HHL algorithms. So more algorithms, more brains to come into quantum, and algorithm developments needs to happen. So and also the hardware. if we can have more qubits, then we can actually simulate bigger problems. That is when we can show quantum advantage there. So I'm actually coming back to the main point of quantum supremacy. So we are not trying to show it's classical or quantum. We are trying to, I mean, at least what I think is it's classical versus classical plus quantum, because quantum alone cannot do today right now. So using classical methods, put quantum over on top of it and try to show quantum advantage. So this is where at least the clients are interested in classical plus quantum, because it's hybrid solutions is what clients are looking for. So clients in the sense the applications basically.
Thank you, Kavitha ma'am. Ricardo, would you like to touch upon your image processing research and future scope of quantum convolutional neural networks if you're looking into it?
Okay. I would like to add a little bit about the quantum machine learning. So I think it's true what Kavitha had said previously. I just want to add that we can also learn something new by studying the quantum machine learning. I mean, there are many new concepts in quantum machine learning that maybe turns out useful to be used also in the classical machine learning. For example, like the tensor networks. In recent year, there is some development of using the tensor networks in classical machine learning, in classical neural networks, that is inspired from the quantum machine learning. So one benefits of studying the quantum machine learning is not just that the promise of the quantum advantage, but I think the knowledge itself can give new inspiration and new techniques in machine learning itself. And yeah, I think that is also one important point that people sometimes forget. And for my previous work in my thesis, uh, I'm not necessarily in that work. I'm not necessarily proving that quantum machine learning can achieve better accuracy or better runtime. Uh, in my work, I give an initial proof that the quantum circuits using the current quantum device with a very limited number of qubits, like by only using 1, 2, or 4 qubits, already can classify the images with accuracy that is comparable to the classical. So it is not necessarily better, and it's also not worse. So it's comparable and about equal, but it shows that with the limited amount of devices that we have nowadays, the quantum computer itself already able to at least performs the same with the classical one. So yeah, it's about my works in my thesis.
I'd like to add a couple of points there. I think this came about in the discussions too, but I just want to bring it in this context. I think many a times the quantum computing is generally considered as something that gives you time benefit in terms of runtime. I think there are a few discussions that happened earlier, but I just want to put that in this context. Is there is a further nuancing that has happened in that runtime benefit is one way of looking at it. The other is quality of results. Can it provide some additional insight into some problem? So say in the case of machine learning, say you have any prediction model. What is your quality of prediction? Can that be improved? Say, for example, in healthcare diagnosis. You need to say predict whether, looking at the image, whether it is cancerous or not. So it's a classification problem. You want to look at and learn and say this particular thing is cancerous, this particular thing is not cancerous. Let's say your prediction quality is say 95%, just throwing out some number. Say if I can push that to 98% or 99%, it means in real terms it can be a difference in the sense of your quality of prediction can become an important metric, not just the runtime per se. In certain sectors, in certain scenarios, that could provide some additional value to the end user, particularly in the space of healthcare, things that are related, that are critical to a particular individual, human, or a society at large. The other thing could be, say, fraud detection, things related to fraud, perhaps. The quality of your prediction to detect something going right or wrong becomes an important metric, not just how quickly can you do it. That is also important, but in some cases, quality of prediction also becomes very important metric to look at.
Thank you, sir. Okay. I think we'll begin taking questions from the audience now. All right, if you have any questions relating to quantum computing, quantum machine learning, or if you're just a beginner, or if you're just curious about this technology, just go to the YouTube chat and ask your questions right away. Okay, I see a few questions in the chat. Yeah. Does the developments of quantum computing influence blockchain technology? If yes, then how? Uh, blockchain plus quantum computing. Shesha sir, would you like to go ahead with this?
Not in the near future. The uh, the encoding decoding part is the part where I at least at this point I can see some intersection, but right now blockchain and the application quantum computing in the blockchain chain space, I don't know of any results that anybody is exploring or research angle there. Doesn't mean it doesn't exist. It just I don't know of anything that's happening at this time. It may be a little early at this time. I think we probably would be looking at problems much more closer than some things that are a little further out at this time.
Thank you. Arun sir or Shalaka ma'am, do you have any views on this?
I think I have seen a couple of discussions around the uh, how to create post quantum cryptography proof blockchains, right? But that's about it. That's the only discussion that I think I have read about recently. From the application perspective, I think blockchain is a really distributed ledger, right? So anything that feeds into the logic of the blockchain is really the compute hungry, and it really depends on an application logic. So if your application logic uh, is such that, like for example, say a supply chain optimization, right? You may be storing the state of your supply chain in terms of which warehouse you are going to use, what contract you are going to trigger. All that can exist in blockchain, but the actual prediction on where an item should go or when it should get ordered can still get triggered on a quantum computer when that becomes available. So I think those kind of synergies would be natural, but that doesn't really mean that it is about quantum computing influencing blockchain.
Thank you, ma'am. All right, let's move on to the next question. Does quantum computing, in your opinion, affect data storing? If yes, how? Okay, before before we answer this question, Shishu sir, I'd like to request you to talk about the illustration which you always give in the IBM talks, wherein how a command goes from the IBM Q experience to the quantum computer and back. I mean, what are the different things involved? I mean, I really love that, and it would be great if you could share it with me.
Right. So that is also these things are evolving so rapidly that you have to contextualize it. So okay, so right now the way the system is as of today is where you have a quantum computer sitting in cloud in the case of IBM sitting in one place there, and then what happens is that you can connect to a particular classical server where you can sort of code things up, and then you say you want to execute it. Then what that does is it then that particular program, say the Python program, gets transpiled into sequence of assembly level language commands that gets then transmitted over the network to the hardware where it needs to be executed. There is a classical hardware that picks that up, and then that each instruction is translated to microwaves that then goes into the particular qubit, and then it runs that. And finally, once you have everything done at the end of the program, naturally you will have some measurements, and then the result of the measurement is again a bit string that comes back into the network through the appropriate cloud servers to your laptop, and you see the final results. So that's the model at this time. This is going to change naturally, right? So what's going to happen in due course is that the model of transpiling everything and having it go and then run and then getting everything back in one sort of way is not the most efficient or the most logical way to do, but it worked when you it is fine when you're starting things out, but the natural extension is you would want to get more the kind of solutions that are likely to provide value or advantage is the hybrid algorithms. So the hybrid algorithms are going to be where part of it is going to run in classical, part of it is going to be in quantum, and in that sense it's going to be more like you transpile and portion of the kernels you identify and run it in hardware. In that sense you would want to keep uh, the machine model that you want to keep in mind is more like how GPUs are in modern day compute. So in GPUs, when you do this compilation or program, you identify core kernels, typically some matrix activity or vector matrix transformation. You then take that, map it to a GPU, run that in GPU, get the result, and the main thread keeps running, right? Much like that, you will have what is called as a QPUs or quantum processing units. You will have a main program, you will try to identify kernels, and those kernels are going to get mapped into what are called as quantum processing units, where it gets executed and get the results back. You're less likely to have end-to-end quantum program that's going to run on all the data set. Back to this question of data storing, it really depends on what is the data you mean. I presume data is meant as a classical data in a machine learning type setting, right? Classical's data currently, the way it is stored in terabytes, etc., it's most efficient right now. It's very hard to uh, um, do uh, do uh, a it's not a quantum information, it's a classical data. If it is classical data, you might as well store it in classical. So the data is less relevant in term vis-a-vis the compute model that you're looking at. If the compute model is going to be hybrid, um, the classical hardware is good with storing data at scale. Terabytes of data you can store reasonably efficiently. You can store terabytes in RAMs too. So the whole memory hierarchy is highly tuned. So the data side of it, at least in the short term, is still likely to be in the classical space. The compute part of it is what is likely to benefit from quantum. And the course of the compute, for example, it could be diagonalizing a matrix or inversing a matrix. Some of those problems which are costly to do in classical at scale, you may want to do those computes in quantum rather than taking the whole data and storing it in quantum, etc. It doesn't mean I want to differentiate. When I say quantum, I mean it in this sense because there are nanotechnology in a broader sense. See, the classical hardware are getting into 5 nanometer realm. They are already in that nanotechnology realm. When I say quantum, I mean qubits, things in qubit side. The nanotech, we are already getting into the nanotechnology space in the classical realm to store the individual bits. So in the short term, I feel the data will still be in the classical. Compute is what we are likely to see in quantum.
Thank you, sir. I really have a clear picture of the entire architecture now, and I'm sure the question was also answered. Okay, we have time for one final question. what are the research areas that combine quantum computing and HCI? So HCI here is human computer interaction or hyperconverged infrastructure. Not really sure. So if we talk about HCI, then uh, would anyone like to take this question up?
Sorry, what is HCI?
It could be either human computer interaction or it could be hyperconverged infrastructure. So hyperconverged infrastructure is nothing but a unified system where it combines all the elements of traditional data storage center, compute, networking, management, everything
Oh,
together.
I see.
And
I see.
yeah,
Okay.
human computer interaction I think can involve the devices that we use to
So
interact
let's
with
assume it's
computers.
the latter, that is hyper infrastructure piece that you are
Hyperconverged
talking about, right?
infrastructure. Yeah.
So yes, that certainly will be an open area of interest, because if we are looking at cloud deployment for this, and then there are going to be some challenges. One is, I mentioned a little earlier that you need to have the kind of algorithms that are likely to be is classical and quantum together. You're going to identify portions of things to run in quantum, and so you're going to go back and forth, etc., and so forth. So there could be many things to look at. One is, how do you deploy these things efficiently? One thing is that we mentioned quantum coherence time is still going to be somewhat finite. It's not like quote unquote infinite as a classical thing. It won't live forever, which means that you may want to do a compute within some reasonable time. And if you have to go back and forth between classical and quantum in some sense, then you may come up with some sort of way where you have your quantum infrastructure, and you may have some servers are tagged to that particular infrastructure, and then you have the larger other compute farm that is available, where through which you use these things. So the kind of problems, you can see some of those challenges, right? Say this quantum hardware is evolved and it can provide some value. Then how do you leverage that efficiently, the quantum hardware, given the cloud farm that you have, the compute farm that you have? How do you layer the queuing mechanism to the quantum? Should it be handled differently? How do you manage them? Benchmarking the quantum hardware will be in the cloud setting, will be one aspect of it, to see what does well, what doesn't do well, how much of would I want to move a lot of data back and forth, how do I do that efficiently? These kind of challenges will come about, and billing and other things will be the next obvious things, right? How do I keep track of the efficiency? Can I multiplex things? These kind of things are likely to come about. How do I tune my infrastructure with this new hardware? That will be sort of something new to look at, because there are certain unique constraints to this hardware I was just telling you about. And how do I manage all of them together is another challenge. And how, as the hardware evolves, it could scale. It may not be in one linear thing, right? So the scaling could be that I have this quantum hardware, these qubits residing in this. I could have multiple layers of this connected through some photonic network, and then it could be within one particular fridge, or it could be two adjacent fridges connected together with different cost in terms of compute, right? Taking the things doing within the same PCB may be faster, easier than converting in, going to the next layer, and maybe even more costlier if I have to go to another fridge and move things around, etc. There could be some of those challenges coming in when you deal things at scale. So there are a lot of things that are still unknown. Some of them are being looked at, like the cloud thing, moving away from full quantum to back and forth type of model. That's the current thing that being looked at. Dynamic circuits is another recent thing that has happened, where things can change dynamically based on the measurement, etc. So some of these features will then open up new opportunities in the cloud setting, how to leverage that more effectively.
There is also a paper on quantum HCI, actually, if anybody wants to go explore. IBM researchers have explored and have worked on a couple papers, actually. So the HCI, one other HCI that Syed was mentioning is human interaction, right? Quantum human computer interaction is something that they're also researching on, to trying to understand current and future users of quantum computers, including the problems they are trying to solve, the domains in which they work, and their workflows to identify gaps in their needs. So one of that is, last 2 weeks ago there was a release on quantum runtime, right? Quantum runtime, what they're trying to do is, if we want to simulate couple algorithms, let's say optimization algorithms like QAOA or VQE algorithms, if you want to run it parallelly for a lot of data, then it's you're working with the user over there, right? So they want to use this HCI, quantum HCI, and want to enable quantum runtime, which makes many of your program run faster. So one of the applications of human computer interaction is how to make it more easier for user to interact with computers, right? So quantum runtime is one of those examples actually, um, to which recently is being developed actually. And the quantum HCI is also part of developing and evaluating education materials, or coming up with new tools for programming and debugging quantum computers, right? So that's QSKIT is one such examples of that. The SDKs, QSKIT is an SDK for interacting with quantum computers and simulators. So quantum HCI is in place already, trying to create new visualization, quantum states. You can also see what is a global phase in the Bloch sphere when you interact with qubits, right? So you can see the positions of the qubits in that Bloch sphere. So that is basically visualization. It's another example of HCI, quantum HCI. So it goes on and on, right? The list goes on and on. If it was quantum HCI on human interactions. Thank you.
Yeah, so I think I've covered both the aspects, human-computer interaction, also hyperconverged infrastructure. Thank you. Well, with this, I think we have come to an end of our Q&A session. Uh, this has really been an extremely informative session for me, and I'm sure that all the other people in the audience have found extremely useful as well. Well, I'd like to thank all the panelists for their awesome insights, and I got to learn a lot. Thank you.
Hello. So
Thank you.
now, as we have come to the end of Q&A session, I would like to conclude the session. I would like to thank every panelist here, Shalaka ma'am, Kavitha ma'am, Arun sir, Shesha sir, and Eraraya sir, for joining us in this discussion and enlightening the participants with all the amazing and informative points covered. I am sure the audience would have got a really great, insightful, as well as distinguished and interesting perspective from each one of you. I would like to extend my thanks to our moderator, Mr. Farhan Ahmad, for bringing up such vivid and thought provoking questions to the table. We are very grateful to have you with us. It's a pleasure to have each one of you take time of your busy schedule and join us at Epsilon 2021. I would like to wish you all good luck and your and endeavors. I hope to see all again very soon. Once again, thank you for joining us.
Thank you.
Thank
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 you.
you.
Thank you, everyone.
Thanks everyone.
Goodbye.
Bye.
Now it's time for today's activity. A link for a Google form will be shared with you in the chat section below. The link contains a small questionnaire for you. You must fill the form and complete today's agenda of points. Attempt the quiz and get a chance to earn 20 points. The time limit for this quiz is only 20 minutes, so gear up and test yourselves. We will have a closing ceremony tomorrow. I hope all of you join and A very thank you to all the speakers who joined the session and all the guests for making this Epsilon 2021 a memorable one. Thank you all the panelists and participants for joining. So, we have reached to the very end of the session. Thank you so much, everyone, for tuning into Epsilon 2021 and hope that you all learned tons from the session today. Workshops, quizzes, projects, and the panelists. Since this is the last session of our event, I would like to bid farewell to everyone and wish you all very good luck for the future endeavors. Our team had so much fun organizing this event and for you all, and hope it turned out to be fruitful for all and just as it was just for us. Thank you so much, everyone. Goodbye.